Hello everyone, so today we're going to talk about kinematics. So what is kinematics? Kinematics is the study of a moving object. Moving object is anything that has velocity, displacement, and acceleration. So what are those terms? Those terms come in the category of linear motion. That's the first thing we're going to talk about here. So the first thing I said was like displacement. What's that? So displacement is very different from distance. Okay, since distance is how far an object has traveled, how much ground it covers basically, and displacement is how far out of place the object is from its initial position. So let's put this in context. So example, we have an object from A going to B and going to C. Okay, the distance would be A, B, C, whereas the displacement, it would be A to C. But writing the displacement as just A to C is not right. Why? Because displacement is a vector quantity, which means it has both magnitude and direction. Okay, distance is a scalar, so it only has magnitude. Alright, so when we say the displacement is A to C, we have to specify it with an angle theta. We can just specify it like theta. The displacement is A to C theta degrees from the positive x-axis, something like that. And so this brings us to the other term, which is velocity, which is simply the rate of change of displacement. It too is a vector quantity. So the thing you should note is that if you multiply a vector with a scalar or divide by a scalar, it will result in a vector quantity. If you multiply a vector or divide it by a vector, it will result in a scalar. It's like a fun fact. So the rate of change means it's delta S over delta t. This is a vector, this is a scalar, so it will result in a vector. Velocity is a vector quantity. The same version of velocity in scalar quantity is what you guys know as speed, but we won't be using that term. So speed is a scalar quantity. So velocity the rate of change of velocity is another definition. What's that? It's known as acceleration. It is rate of change of velocity. So it's delta V over delta t. It is also a vector, and time is a scalar, so it'll be a vector. Alright? Okay, so let's go to the graphs. We can represent all this in graphs. So the first graph would be a time and displacement graph. And the second one would be a time and a velocity graph. We can make the velocity there. And the third one would be a time and an acceleration graph. Okay, let's make it like that. So the first thing we do is, let's say, we're gonna go with stationary. Stationary is basically the easiest because it's just a straight line. Because it doesn't move, it's not displaced, it has no velocity, and it has no acceleration. Well, mostly it has no acceleration. In other cases, there might be acceleration. We'll get to that. And the second case is constant velocity. Constant velocity, the displacement time graph will look like this. Okay, and the velocity will look somewhere around like this because it's constant. If you notice, the gradient of the displacement time graph would be the velocity. Since this is a constant gradient, the velocity is constant at some value velocity constant. The acceleration is also the gradient of the velocity. So velocity is the gradient of the displacement, and acceleration is the gradient of the velocity. Alright, so acceleration would also be 0. Assume that that's 0. Okay, this is constant positive velocity. What would a negative velocity look like? If constant velocity negative, we'll use this color. The displacement would look something like that. Okay, the velocity would be negative, somewhere around negative VC. Okay, and acceleration would still be 0. Right. Now we'll go to the fun part, which is increasing velocity. In the graph, it would look like this. And since velocity is the gradient of the displacement time graph, we can see a constant increase in gradient. It will look like this. Alright. And acceleration, on the other hand, is the gradient of this velocity time graph. So it will be at this AC and a constant acceleration over here. Alright. What about decreasing velocity? Decreasing velocity will look like this. Okay? And the velocity is decreasing, so it goes from a certain point down to 0. The 0 point here is when the gradient reaches 0 here. At this point, it's a straight line, so it reaches 0. Right? And the acceleration would be a constant here, negative acceleration. Alright, so let's go back to this thing called stationary. I said earlier that a stationary object might have an acceleration of 0 or not 0. So when or how does this work? Here. So we'll talk now about projectile motion. Projectile motion is like when you throw something, or when you kick a ball, let's say. When you kick this ball from the ground, you kick it this way. The path it'll travel is like this, a parabolic motion. And how we can solve for this is we consider this as two velocity components. So this is v, and you make it vy and vx. Alright, with no air resistance, Vx will be constant throughout the whole thing, so it's a constant motion. Vy has acceleration, where it's due to gravity. So there's the acceleration due to gravity there. So Vy will slow down until it reaches this point, its maximum height. In here, it's instantaneously has a velocity of 0, but it still has an acceleration of the acceleration due to gravity, 9.81 meters per second squared. And once it goes down here, it will have increasing velocity as the acceleration is in the same direction as the velocity. This one's slowing down because the acceleration is opposite to the velocity. In here, the velocity y will start going down and acceleration is both going down. Alright, with air resistance, it's a bit more complicated. With air resistance, Vx would decrease because there will be a constant drag wind force on the ball here, right? There's an acceleration from drag. Vy would basically, when it falls, increase to a maximum value. So the first thing about the air resistance of Vy, it won't reach as high because the air resistance will act the same down. Air resistance or friction, drag force, always acts opposite to motion. So if it's going up, Vy is pointing upwards, right? And so the acceleration is pointing downwards. Once it reaches its maximum point, there's basically no air resistance at this moment, instantaneously. But once it goes down, there will be the moment it goes down here, the air resistance would go upwards. So then, once it falls, the air resistance would go upwards until, like, the force of friction, for the drag force, will be equal to F drag will be equal to F of the weight, meaning there will be no force, and since there is no force, there will be no acceleration. So it'll reach a maximum value of velocity called terminal velocity. We can represent all this in a graph. So let's say we have there we go. This is T, S, V, A. So once it normally falls, this is just talking about the vertical. So let's not assume this ball. Let's just assume someone dropped a ball, then it's falling down. That's the initial, and the ball will land here, something like that. Okay, goes down. So without air resistance, this displacement and time would look like this. The velocity would just keep on increasing like that, and the acceleration is constant because it's the acceleration due to gravity. But if we have air resistance, we have to consider this terminal velocity thing. So the S will increase till it reaches a constant gradient. Like this point would be constant gradient. So how we represent this is as there. And this value would be the terminal velocity. Okay? The acceleration at this point, this gradient is 0. So acceleration must at one point reach 0 there. So this is, the blue one is with air resistance, the yellow one is without air resistance. Alright, so that's it for today. Kinematics is both linear motion and projectile motion. That's it. Thank you.